The last two parts of section E2 are to do with different types of stars and the Hertzsprung-Russell diagram. We'll start with different types of stars. Types of stars. Now, we have red giants. There are two things you need to know about red giants. First thing, they are red. Second thing, they are giant. So, why are they red? They're red because they're very, very cool. The surface temperature could be 3000 Kelvin or something like this. And they're giant because they're very large, which means they're going to be fairly bright. Remember that the luminosity depends on the area of the star. Normally it's one of the final stages of the evolution of a star. And it's basically when helium starts to get fused into other elements rather than hydrogen into helium. It's helium is fused into other things. Here we have a red giant, which is Antares, which is actually bigger than the orbit of Mars, to give you an idea. This is the Sun as the main part of a star, and this is the Sun as it will be when it becomes a red giant. So it's going to be somewhat bigger than it is now. In fact, it's going to be so big that it's going to engulf the orbit of the Earth and Mars. But not yet. You have to wait 4,000 or 5,000 million years time, so there's nothing to worry about just now. Other types of stars. White dwarfs. There are two things you need to know about white dwarfs. One is that they're white. That means they're going to be very hot surface temperature. The second one is that they are dwarfs, which means they're very small, which means they're not very bright. They might have a very high surface temperature, but they're going to be fairly dim because the area is so small. And it's usually what's left after the star has almost died. In white dwarfs, you don't really get any nuclear fusion anymore. It's what's left after a nova or a supernova or whatever, depending on the size of the star. Luminosity, well, basically, if it's got such a small area, it's going to have a very low luminosity. This is a white dwarf, which is very, very small, even though there's a very high surface temperature. The white dwarfs might have masses comparable to the Sun's, but their volume is much smaller, even as small as that of the Earth, which means they're very dense, but because they're very small, they're not very bright. Other types of stars, neutron stars. Okay, these are not, strictly speaking, stars, but they radiate a lot of energy, and they're mostly made of neutrons. It's basically what's left after a very massive star, and it consists mostly of neutrons, but it's very, very hot and is able to radiate, but it's also very small and very dim. Pulsars, these basically pulse. They're like lighthouses, and they're understood to be rotating neutron stars. And because they rotate a bit like a lighthouse, and they send this beam of radio waves and a bit like a lighthouse. And the period of oscillation can be a few seconds to a few milliseconds, so they spin very quickly. Okay. Next one, supernovae. These are basically stellar explosions, and they're very large, so they're very bright. Sometimes they can be so bright they can outshine everything in the galaxy. It's basically an explosion that the star expands, or the outside expands so quickly, the volume increases so rapidly, the high temperatures and high areas, it means that it's a very, very large, a very bright. This is an example of what was a supernova, and this is what's left of it. It's called the Crab Nebula, and it was basically a star, which is around here somewhere, and it exploded around 1,000 years ago, and this is what it looks like now. This is what's left of it. At the point where we believe the star came from, there's a pulsar pulsing away. Supernovae. A supernova causes a burst of radiation that can be very, very bright, but it doesn't last for very long. Black holes. These also not, strictly speaking, stars. We don't really completely understand what they are. There ends up being a kind of mathematical proof of what it is. So it's basically a regional space where gravity is bent so much, it is so dense that light is not able to escape, so it's black. The line over which light is not able to move is called the event horizon. We can't see things that go on beyond this line. So it's comes from the idea that it's black. This is what you need to know of a black hole. Forget the whole part. It's black. It's black. Radiation is not able to be emitted from inside the black hole. It is emitted from outside the black hole because objects are falling in towards it and they are able to radiate. The next thing, this is an important thing, the Cepheid variables. These are stars which have very clear luminosities in the sense that they have a regular variation in luminosity which depends on their brightness, and if you know how the time period for the change of luminosity, then you know the luminosity, you can find out how far it is. They're used to as benchmarks to find distances, or standard candles they're called. Okay, so they're called standard candles. If you know the period, you can work out the absolute luminosity, and therefore you can work out the distance. It's a very giant yellow star, and it expands and contracts. What will happen to the luminosity? Well, basically, as it gets larger, it becomes brighter, because the luminosity is to do with the area. The luminosity of Cepheid variables is 10 to the 3, 10 to the 4 times that of the Sun, so they're much bigger than the Sun. Okay, binary stars. Most stars, or a big proportion of them, are actually binary stars. There are two stars together which they orbit each other. And if you're able to see how quickly they move relative to each other, you're able to work out what their masses are. Here we have a binary star, but you see one star, the binary is there, the secondary star is there. Okay, three types of binary stars. Visual binaries. These are the clearest because you can see the two different stars. You can see how quickly they orbit each other. You can easily determine the time period. If you know the distance between them and you know the speed that they're moving at, then you can work out their masses easily enough. So it helps you to solve many problems about finding out the masses, the distances, and so on. Okay. Eclipsing binaries. These are very interesting because you have two binaries that are so close together that you can't actually distinguish them, but you can see a periodical change in the luminosity, in the brightness. Here we go. Now, here, for example, we have the two stars. You can see the light from this one and the light from this one, so we get a maximum brightness. What happens here is that the dimmer star goes in front of the brighter star, so there's a big drop-off in the luminosity, in the amount of brightness that we see, because this is blocking some of the light from this one. Here we have the same thing again, but the brighter star is blocking the dimmer star, so there's only a smaller change in the luminosity. Here we have another example here, which we can look here. We have a very bright star, very hot star, orbiting a red giant. Now, for most of the time, we can see the light from both of the stars, so we get the maximum value here. What happens here is that this hot star moves behind the red giant, so because all the radiation from this is lost, then there's a significant drop in the light that we get from that star. When it comes around the other side, then the light goes back up again to the maximum level. Here we get a smaller drop in the luminosity, because we can still see the light from this star, but there's the light is obscured from behind it, from the larger red star, which, as you know, is going to be cooler, so each meter squared is not going to be as luminous. So there's a smaller dip here. Here we get the maximum luminosity as it moves in front to the side, and then we get another big dip as the brightest star per unit area goes behind the red star. So this is why we see this variation in their brightness. Other binary stars are spectroscopic binaries, and we know that basically because when one of the stars moves towards us, its spectrum will be blue shifted away, it's going to be red shifted, and so on. And to do the calculation here, we know that the original wavelength minus the observed wavelength, which will give the shift of wavelength, divided by the original wavelength, will give the Doppler shift. Okay, so this is going to be a small value divided by a large value, which is the wavelength of the light. So you're going to have a tiny percentage of Doppler shift, and this will be equal to the ratio of the speed of the star divided by the speed of light.